So now it is my pleasure to introduce Kelsey Allen, who's an expert in physical reasoning and natural and artificial intelligence. So Kelsey is an assistant professor of psychology and computer science at UBC and one of Vector's newest faculty members. Prior to joining Vector and UBC, Kelsey was a senior research scientist at Google DeepMind. She received a PhD from MIT in brain and cognitive sciences, and we are delighted to welcome Kelsey back to Canada. Her work has received numerous awards, including the International Glushko Prize for Best Dissertation in Cognitive Science, a Best Paper Award from Robotics, Systems, and Science, one of the top conferences, and an NSERC PhD fellowship. Spanning robotics, machine learning, and cognitive science, her work aims to elucidate the mechanisms that give rise to adaptive and efficient learning, especially in the domain of physical problem solving. Without any delay or further ado, please join me in welcoming Kelsey to the stage.
All right. Hi, everyone. Thank you very much for having me. I'm Kelsey, and as Dan just introduced, I just started at UBC. My lab is called the Natural and Artificial Intelligence Lab, or NAIL for short, and I'm also one of the newest members of the Vector Institute. So my work, as Dan sort of hinted at, is very much inspired by natural intelligence. Most of my PhD was on natural intelligence, and one of the things that natural intelligences have to do every day in order to survive is solve physical problems. And some of our smartest animals can do these things in pretty amazing ways. Like this crow, for example, was this very weird problem of how to get this food out of this tube by dropping in blocks in order to try to raise the water level. But as humans, we go way further than this, right? Actually, most of our world is full of the different tools that we've created and have passed down through generations in order to make our lives easier. This is one of my favorite examples from a biomedical engineer who's created this artificial lung, which is being implanted by these expert tool users, surgeons, in order to allow a patient to breathe. And even if most of our tools have been passed down through generations, the sort of spark of innovation to repurpose an object as a tool really exists in all of those. So this is an example of a young boy with the very important problem of acquiring that tasty out-of-reach Easter egg, and he has this sort of innovative idea to try to use a shovel to do so. He's extremely persistent, right? He uses the shovel in an unusual way from both ends. Unfortunately, in this case, he's just scooped by another agent with an unfair height advantage, but I'm sure that this innovation is going to help him in future. By contrast, what we have currently in terms of physical intelligence is not nearly so adaptive or efficient. Now, this is a policy rollout from Physical Intelligence released just a few months ago, and this is what's called a vision language action model, which was trained on literally hundreds of millions of time steps across 68 tasks, and then further fine-tuned on 100 hours of data from this specific toast task. And yet, as soon as this toast falls outside of the distribution that this robot has experienced, it has a very hard time recovering from that, and basically just fails to complete the task. So, what is missing from this picture? How do we get more adaptive intelligence like the crows and the humans that we have in the natural world? So my research aims to understand how humans and machines build world models, which I think are necessary for adapting to these out-of-distribution cases, and then how to use those world models to enable problem solving and innovation. And all of this exists among an ongoing question, which is sort of pervasive and has already been hinted about, which is how much can you get away with just scaling up the data that you have access to, or do you need fundamental structures that sort of guide the ways in which that data is used and interpreted within the machine learning models themselves? So the talk outline today is going to cover 3 areas of work that I've been working on. Most of this has happened at Google DeepMind, but these are representative examples of what I'm hoping my lab will work on at UBC. The first is, do these internet-scale but totally unstructured video models that you might have seen like Sora or Veo or all of that actually learn things that look like physics? Second, we'll look at how to learn physically realistic world models using minimum amounts of structure but also a little bit of data. And then finally, I'll talk to you about how we then use these models to enable problem solving and innovation. So first up, do internet-scale, unstructured, generative video models learn physics? Now, this is a question that people have been looking at for at least a few years. And it generally involves basically creating a real or synthetic data set of different kinds of physical scenarios, and then comparing predictions from generative video models such as Sora to ground truth rollouts of each of those videos. So these are two recent examples of physics IQ and fission that have come up in the community over the past couple of years. But these kinds of approaches actually have a pretty important problem that is not easy to solve by just assuming that you have access to ground truth. For example, many possible physically consistent futures can exist from the same conditioning information. So if you condition on these first two frames, there are actually a variety of ways that this scene could unfold. And in this case, the video on the left is the real video, and the video on the right is the generated video. But the video on the right doesn't appear particularly physically unrealistic, right? It's just sort of a different way that this scene could unfold. And then if you were to actually try to compare these videos, it would look like it had a very large error. These generative video models also can produce videos based on only language conditioning information, right? And it would be very difficult to actually recreate these in a real setup. So this hydraulic press, for example, was created using the prompt, "A hydraulic press crushes a glass ornament." And the one on the right was someone is manipulating, I think, a piece of paper. And there's just no way we could easily recreate this to get a ground truth. And yet you can also determine that the hydraulic press crushing the glass ornament does look a lot more physically realistic than these hands that seem to morph in and out of existence over time. So the question for this project was, how can we evaluate videos for physical realism without access to ground truth? And what we did was we created a model, a self-supervised motion model called Trajan, which is an autoencoder trained to reconstruct point trajectories, with the idea that actually modeling just the motion is the most important thing to do here. So the way Trajan works is that it takes input videos, they can be real, they can be generated, and then it uses an off-the-shelf point tracker to get point trajectories for different parts of that video, shown as these little rainbow sort of colored moving positions. What it then does is that it drops out a subset of those rainbow points, which are now shown in black on the top and bottom, and runs that through our trajectory autoencoder, which is just represented as a big transformer model, and tries to decode those missing black trajectories conditioned on the rainbow ones through a compressed bottleneck within this autoencoder. What you can then see on the right-hand side is the estimate of the reconstruction error for each of these two videos, where in the top case, because this is sort of looking realistic in terms of the motion, it's very well reconstructed, whereas in the hands case in the bottom, where these things are morphing in ways that are very unrealistic, it gets very poor reconstructions. The reason we see these differences is because Trajan is trained on thousands of videos from YouTube, and so basically motion that is within the realm of realistic videos is going to be well reconstructed. Motion that lies outside of that will not be. We compared this trajectory autoencoder model to a few others that are very popular within machine learning. One is this video MAE model, where instead of dropping out point trajectories, it drops out image patches and tries to reconstruct those in order to reconstruct a video. Another is from NeurIPS this past year. It's called Moog, and it's basically a model for trying to predict the next state of the video in this latent representation. And the last one is an older model for action recognition, which takes in a video and then tries to predict the action that's being depicted in that video. And what we measure is a sort of entropy over the action class label. So if the video doesn't look like it's depicting any particular action, then it's going to have high entropy. If it looks like it's depicting a particular action, then it'll be low entropy. We then collected a data set of human-evaluated realism on over 1,400 unique videos generated from 10 different open-source generative video models, and we collected 5 ratings per video. And people here rated the motion consistency, appearance consistency, and overall physical realism for each of these. If we look at what these realism ratings look like for this data set, this is supposed to be rated on a scale of 0 to 100. But you can see not even a single video from the data set was actually deemed by raters to be truly realistic here. And in fact, the mode here is about 50. So things only look sort of about half half realistic, suggesting that these models are nowhere close to capturing sort of physically realistic dynamics. But within that range, right, there's a lot of variance. So we wanted to look at how each of the different models I presented actually captures human ratings of realism on this data set. So what we did was we correlated human ratings on each of the videos to the reconstruction or entropy errors from each of our models on each of these videos. And in all cases of motion consistency, appearance consistency, and realism, the model that is trying to reconstruct point trajectories, so very focused on motion, does the best job in explaining sort of what people find most realistic and what people find most unrealistic. And you might say, so these correlations could be as high as 1, right? So the fact that they're only 0.3 is very, very low. But actually, if you just correlate humans to each other, they're also not particularly consistent. So in this case, if you just take 50% of your humans and try to correlate them with other 50%, you actually only get correlations of between 0.4 and 0.55 here. So this means that in the case of the motion and appearance consistency measures, we're actually capturing almost all of the variance that we could possibly capture using this point trajectory model. The one exception to that is this realism column, where we're only capturing about 50% here. And I'm going to show you why on this next slide. So this is a very weird-looking soccer ball, right? But actually, from a physics perspective, this soccer ball is just hanging out. It's not moving. And so really, this is actually physically realistic, even though its appearance is very unrealistic. And so all of our models actually score this as very realistic because they're focused on the motion. But people tend to score this with low realism, physical realism, presumably because the soccer ball is very outside of the distribution that they've experienced in their lives. So to summarize the section, these open source generative video models do not yet generate videos with good consistency or realism despite internet scale training. This point trajectory model best captures human evaluations of consistency and physical realism, and humans sometimes struggle themselves to separate physical realism from priors about realistic appearance. So given that these large-scale models don't seem to be able to learn super realistic physics models, we're next going to turn to a class of models that can. And this class of models is very much inspired by humans, and in particular infants. So for a very quick introduction to some developmental psychology for some of you in the audience, infants seem to have notions of objects, object permanence, and contacts basically as young as we can measure. People have looked at this in 3-month-old babies, which I imagine is very hard to do any experiments on 3-month-old babies. And they find that they do have these notions of permanence and contacts, even already at that point. But there are other aspects of physics that young children don't understand until a little bit later in life. So for example, they don't understand that the shape of an object is going to determine whether or not it could sit stably on top of another one. This sort of detailed understanding of physics doesn't seem to emerge until later once they've had some experience with the world. So inspired by this, graph network-based simulators, or graph neural networks, are trying to take these ideas of objects and contacts and relations and bake that into a neural network architecture. So in general, we're baking in this sort of idea of 3D space, objects and relations, and then trying to learn the rest of physics from data using neural network representations. The way this generally works is that you put your scene of physics into a graph-based representation. So for example, in this case with the fluids, the graph encoding is shown at the bottom here, where each different particle within the fluid is represented as a different node, and then edges are connected between fluid particles or between nodes when those two particles are close enough together in space. The graph network simulator is then going to take 2 graphs of 2 different physical scenes across 2 different time steps and try to learn to predict the next time step given those previous 2. You can also use the same kind of representation of a graph on things like solid objects by taking their mesh topologies and taking each different mesh vertex as a node, and the triangles, the mesh triangles as the edges, and all the same kind of thing applies. What's really cool about graph networks is that across a lot of work now over the past few years, we've been able to show that they work for a very large number of different kinds of physics. So these are all rollouts from a GraphNet simulator that's learned. These are not rollouts from an analytic simulator. So it's able to capture very well fluid dynamics. It can capture different kinds of cloth dynamics. And over the past couple of years, we've also shown for the first time that they can capture very well very complex rigid dynamics. The other super cool thing about graph networks that makes them really useful is that they display extremely powerful generalization way outside of the training data. So for example, if you train a GraphNet simulator on just throwing 10 objects of just 10 different shapes together on a table, you only ever see 10 different shapes in training. It's only this cube, these sort of weird spheres and weird interconnected pipe things. But then without any further training, you can generalize to having, any scanned 3D object from the real world. You can also drop into the simulation, and you'll get very nice physical predictions. And you can also generalize to many more than 10 objects, even more than 300, which we showed in a recent NeurIPS paper. But one thing you might want to ask yourself, and this was sort of brought up in the last talk, is actually, given that these simulations look so good, do we need to learn physics at all? Why don't we just use the actual given simulators? And the reason for that is that there are some kinds of physical dynamics that are important for robotics that are actually really hard to model with analytic simulators. So this is a very simple task of just tossing a cube onto a table. But actually, the physics of contact dynamics can only be solved precisely if you go down to the quantum level. And so the analytic simulators that we have, models like Drake here, which are probably the state of the art in robotics, cannot fit this data particularly well. If you look at this cube toss, the gray is shown in ground truth, and Drake is shown in blue. And even if we fit all of the available parameters in this Drake engine, things like the elasticity, friction, and mass of the object, you simply cannot capture these kinds of contact behaviors. By contrast, our graph neural network simulators here can do this really, really well. So this GraphNet simulator is trained on this real cube data, only about 256 trajectories of it, so not actually requiring that much. But it does a very good job, as shown in blue, of predicting the movements of the cube, shown here in green, which is quite encouraging. You can also look at that quantitatively instead of just qualitatively and compare it to how different robotic simulators can do, again, with their parameters tuned to the specific scenario. And here the GraphNet is shown in blue, with the different robotics models shown as these dashed lines. And we varied the amount of training data that we gave the GraphNet simulator and saw how it compared to these different robotics models. And what we were very excited about here is that even with as few as 32 trajectories of real data, right, only 32, no pre-training, the GraphNet is already outperforming all of these robotic simulators for this cube tossing task, at least in its rotational error. And if you go up to 256 trajectories, you get the same in the positional error. You can also connect these graph neural networks to perception using inverse graphics pipelines. Here, what we have is a model called visual particle dynamics, which instead of requiring access to the 3D ground truth state of a system, can just be trained with multi-view RGB depth cameras. And here you take multiple RGB depth cameras, take each of the images from that and encode them into a 3D space, run a GraphNet simulator within that 3D space to predict the next time step, and then re-render that into images for each of those different cameras. And now you can train this thing from images to images without ever needing access to the 3D state. So we trained this model on these different kinds of squishy objects interacting with each other. And what's quite cool is that because we have this sort of latent 3D representation, we can actually do things like latently edit the 3D state. So in this case, the original trajectory looks like this, where you have these two squishy objects interacting with each other. But we can do things like delete the cylinder, and the ball will still fall without having any deformation until it hits the ground. Or you can actually do something like delete the floor, which is way outside of the distribution that this thing was trained on, and both objects fall together without either one of them deforming. Again, showing sort of the power of these models to generalize beyond the training data that they had access to. So to conclude this little section, graph network simulators generalize to many different kinds of objects, new object shapes, and new numbers of objects. They can be more accurate than these handcrafted analytic simulators, which are state-of-the-art in robotics when they're applied to real data. And they can be connected to renderers to learn directly from videos, which can support 3D editing and other capabilities. So now in this last section, I'm going to talk to you about how to use these GraphNet simulators for actually solving problems and innovating new objects. So this problem of tool use and tool innovation was actually the main thing that I was interested in for my PhD, but more on the human side. And the reason that I find this so compelling is because most of our world is full of these objects that we've created. And it sort of spans this whole range of everything from like this daily human reasoning, like we have a good time just playing these different kinds of phone games where you have to draw a tool on a screen to get fluid into a cup to make the cup happy, to these really big problems in engineering and innovation, like designing landscapes for farming or irrigation, or even designing planes. And so in this project, we wanted to understand whether or not we could create machine learning models that can design new objects sort of inspired by these human motivations. So we have problems where you have to draw a tool on a screen in order to get blue fluid into a yellow area, or shape the height field of a landscape in order to move water into different magenta pools, or even design extremely high precision airfoil wings. What we have is our GraphNet simulators, and we just trained them on next step prediction with data that's randomly obtained from the world. So for example, we could train the GraphNet simulator on just these 2D giant blocks of fluid that are interacting with just a few different line segments, and then we want to understand whether or not we can use them to actually design containers and funnels and all this. When we use those dynamics models for design at test time, what we have is a design function that takes these design parameters phi, in this case phi is representing the height field of this landscape in green, and some initial scene configuration alpha, which in this case is a pipe coming off the wall, and that creates our initial scene that's shown here on the right, which can also be represented as a graph. We then use the GraphNet simulator that we've already pre-trained to roll out how this should unfold over multiple different time steps. And then on the final time step, we can calculate the reward, which is parameterized by theta r. Theta r here is just, for example, the location of these two magenta pools that you're trying to get this fluid into. If we actually roll that out in practice, we start with some random initial design, and then we continue to refine that until we have a design that accomplishes the task as well as possible. Now, the different optimizers that we could consider using for this are inspired by sort of different approaches in engineering and graphics. The first thing that's very commonly used, especially in engineering, is just gradient-based with analytic hand-designed models. These models are particularly important in settings like aeronautical engineering, where you can actually just write down the equations of motion that each have their own well-defined gradients. And this allows you to use very powerful gradient-based optimization tools in order to design things efficiently. However, it's not always easy to write down these analytic models with gradients. Sometimes we might not know what the gradients are, or it might just be very time-consuming to do so. So in machine learning, the alternative that people often approach is to use sampling-based optimizers, and then you can use whatever black box, forward, neural network, dynamics, whatever you want, function within that optimization loop. And this works very nicely because you can use it for any kind of dynamics you want, but it doesn't support high-dimensional design because sampling from a very large space of possibilities can be extremely expensive. So what we were looking at was whether or not we could use gradient-based optimization methods, but with the gradients that actually come out of the graph network simulator. If we can do this, then this will allow us to do very high-dimensional design problems because gradients give us a lot of global information to which we can use to direct what our design should be. but it also would allow us to actually use general dynamics because we could just train a GraphNet simulator on the data and then get something that's parameterized as a neural network and differentiable. But of course, the big question is whether or not this can work. And I want to just take a moment to pause and tell you why you should expect what I just told you to fail. The first reason is that graph neural networks, just because they're defined as neural networks, so in theory they have gradients, that doesn't mean their gradients are actually useful for anything. And in fact, there's been a long history showing that these kinds of models can have exploding gradients or vanishing gradients or just simply useless gradients. And so they might not be helpful at all for optimization. They can also have very large propagating errors, right? So these graph neural networks are trained to only predict one time step into the future. But then in these design tasks, we're asking them to predict hundreds of time steps into the future. That means if any one of those steps has an error, it's going to be propagated literally 100x before it reaches what we would calculate the reward on. And therefore, it might just not be giving us a very good estimate of what the true design power of that particular design is. And the last issue is that for neural network models in general, as was sort of already mentioned in the prior talk, if you push them too far outside of their data distribution, they can come up with what we call model hallucinations. And this is particularly problematic in an optimization setting because you're actually trying to find a design that's better than anything that you saw in training. So for example, what you can get is really good predictions between the predicted reward on the y-axis and the actual reward on the x-axis when you stay inside your training distribution. But when you try to use this thing to actually find a new design outside of the training distribution, you get these orange stars in the vertical direction, which are, in terms of actual reward, not actually better than anything you saw in training, even though the model thinks that they are. But with all of those caveats, graph neural networks actually turn out to be very useful and have very useful gradients for solving some of these different design problems. So this is the design procedure unfolding for this 2D fluid tools environment, where you have to draw an object on a screen in order to keep the blue fluid in a particular yellow region. And this approach can, create containers, it can create ramps, and it can create funnels. By contrast, if you use a sampling-based optimization procedure, you get worse reward overall in terms of how well these designs actually work. And you don't get particularly smooth or sort of comprehensible designs either. They sort of are random because, again, they're just they're just sampled from a larger distribution without sort of using this gradient information to smoothly arrive at a solution. If you look at the overall rewards, the gradient-based optimization procedure through the graph nets gets overall better reward than the sampling-based one, which is unsurprising given those optimization traces. But perhaps more surprising is that it also does better than a sampling-based optimization procedure when you use the true simulator for the optimization. This means that in these particular problems, the actual search space is harder than the issues that might prop up during rollouts from errors. So the graph-based neural networks here are accurate enough that they can actually outperform a true simulator here, which is pretty crazy. We also looked at scaling this up to a much larger design problem. Now you have 625 design dimensions in this landscape task. And here you see a really, really huge advantage of using the gradient-based optimization techniques through the graph neural network simulators here. They tend to outperform the sampling-based approaches by 1 to 2 orders of magnitude. And finally, perhaps most interesting from industrial use case perspective, you can also use these GraphNet simulators to do design for tasks that have been extremely highly engineered in engineering domains, such as airfoil optimization. So here, defoam is a particular engineering-based industrial model that has one of these analytically defined differentiable models. And it's able to achieve an airfoil wing here that performs with about 1.74 reward. But just using the gradients through a graph neural network, as shown on the right, actually does just as well in terms of finding an airfoil wing shape here, which is pretty impressive. And it does so 16 to 48 times faster than you can get with these commercially available engineering solutions. So in summary, for the graph networks for design, These graph neural network-based learned simulators support general-purpose design over complex physical domains. Training these just generic dynamics model still allows you to do this extremely out-of-distribution design. And we can even match the accuracy of specialized commercial solvers in engineering for airfoil shape optimization in a fraction of the time. So overall, today I've presented to you 3 different projects. First, Trajan, this motion autoencoder, which allows us to measure motion realism in generated videos. Second, I talked to you a little bit about GraphNet simulators, which can learn physically realistic world models, given minimal amounts of structure and also minimal amounts of data. And these GraphNet simulators can also be used for high-dimensional design problems that are relevant for both industry and science. I just want to finish by sort of talking very briefly about upcoming work that's coming out in the next, I guess, couple of months that I'm pretty excited about, and that I think if you're interested in any of these topics, please reach out to me. One is that we've been working with industry partners on doing multi-agent coordination with graph neural networks for settings that are really relevant to manufacturing, where you have multiple robots that all have to coordinate together in a single area in order to solve a problem. That's going to be in science robotics soon. I've been working with collaborators at Google DeepMind on how to extend diffusion models to allow them to be able to support editing in 3D with either depth conditioning information or bounding boxes. And I've also been working most recently on sort of cognitively inspired interactive reasoning with both vision language models and large language models, and we have some work in submission on that now. So thank you all very much for listening, and thank you to my collaborators, I think pretty much all at DeepMind for this particular presentation. Again, I've just started, and I'm looking to collaborate with folks, so if any of this sounds interesting to you, please do reach out. I'm happy to take any questions.
All right, fantastic presentation, thank you. We have time for questions.
Yeah, so my question relates to the use of human annotators to validate some of these models, which you talked about in the first part of the talk. I've seen, in terms of generative models for static images, this like hyper-realism effect where sometimes, for example, like images of synthetic images of faces can be perceived by humans as more realistic than actual photographs. So does this relate, how does this affect your work? And you mentioned also the inter-annotator disagreements. I kind of wanted to get your perspective on the outlook of human annotation as a way to validate and maybe limitations of that approach.
Yeah, that's a great question. So the question was about sort of perspectives on human evaluation and sort of the pitfalls and comparisons to some of the very, very interesting work on hyperrealism in images, and also where some of the discrepancies come from within the human ratings. On the first point, I think that that's very much something that could occur, and like with things like hyperrealism, for example, in video models eventually, but we are not yet there. And I do think that one thing I'm particularly interested in understanding, so this is sort of answering your second part of the question, there do seem to be major differences between humans in terms of how much they care about like the appearance realism when actually evaluating the motion. And so some people are able to sort of separate these two things very well. So something can appear very unrealistic, but then the motion looks good, so they're happy with that. And other people seem to couple those a lot more together. And I don't know exactly why that's happening. I actually think that's a very interesting cognitive science question, because there are many things which we can perceive like cartoons that we know are not like appearance realistic, but still appear physically completely fine. But somehow this is maybe striking the uncanny valley for people, and they're getting tied up in similarities between those two things. So I do think that there's this whole science about like people's perception that is actually super interesting from the perspective of how to evaluate generative models that has not yet been explored. And the main reason, the main way that people actually tend to compare generative video models is in these pairwise comparisons, where they have a video generated by one model and a video generated by another model, and they ask people to just say which one looks better. But actually, I think that that's fairly limited in terms of like what you would actually want to see, because, for example, you can't make two videos that are conditioned in exactly the same way, for example, so it's hard to compare them. So I think it's a really sort of interesting question for future work, and I don't have answers yet, but I think that's sort of where the research is going. Thank you.
Next question here.
Thank you. So in cognitive behavioral therapy, cognitive distortions are corrected through a structured cognitive frame provided by the therapist. In transient, how does the model self-correct when its learned physical reasoning deviates from realism? Does it employ intrinsic self-supervised mechanisms such as predictive error minimization, constructive learning, or something like consistency checks across different sensory modality to refine its understanding of physical interactions?
Yeah, great question. So the question was about sort of generally what is Trajan doing in terms of how it's learning something like physical realism, and does that map onto like theories from cognitive science about how people might do something similar? And the answer is it doesn't do anything interesting at all, actually. So it's just a model that's trying to reconstruct point trajectories. So it's not doing any kind of intrinsic motivation. It's not doing any kind of exploration. It is using predictive error because it's trying to essentially, if it's not doing a particularly good job at predicting how a point trajectory is going to unfold relative to what it's given, then it's going to make a gradient update from that in order to try to have better neural network parameters. They're going to do a better job of that in future. But otherwise, that model is only cognitively inspired insofar that it's tracking motion rather than tracking pixels. And as I sort of just mentioned, it's actually not obvious if that's the right approach longer term. We sort of hypothesized that it would be initially, but it does seem like people couple these two things more than we necessarily expected. And so it might be important in future to think about models that both predict the appearance as well as predicting the motion. And that would sort of be follow-up.
I have a follow-up question. So how does transient ensure its corrections lead to robust and generalizable improvement rather than overfitting to specific motion patterns?
So we look at that by basically just training it on as much data as we can. So in this particular case, because this model was developed at Google DeepMind, we were able to train it on hundreds of thousands of YouTube videos that are just filtered to make sure that they have motion in them at all, and then also filtered to try to remove situations where you get like a scene cut, right? So like if you're going from an indoor scene and then you go to black and then go to an outdoor scene, we also remove those from the training. But the main way in which we get it to not overfit to motion patterns is simply to train it on a lot of data.
Got it. Thank you very much.
Thank you.
So I'm going to briefly check if we have any questions online. No questions online at the moment, so we'll hop back in person. Do you have a question?
Yes, I do. I think
Can you move a bit closer to the mic?
I think your research is fascinating. And we're actually, at RBC, we're exploring graph database, and this is a very good use case. And I was wondering, for your graph network-based simulators, is it computationally intensive? The reason why I'm asking is, when I was doing my PhD in engineering at U of T, a lot of the work on optimization was theoretical because it was so computationally intensive.
Yeah, it's a great question. So graph nets are surprisingly not very computationally intensive, actually. In what I showed with respect to the more common architecture now, which is a transformer, graph nets are actually more or at least equally efficient. There's an equivalence relation between them if you do all the math, but they're very similar. You can make graph nets more expensive by doing multiple rounds of what's called message passing, if you ever sort of came across that before. But basically, you run a message passing algorithm to try to pass messages between different nodes in the graph. And depending on how many rounds of message passing you want to run, you can make it arbitrarily expensive. But in the cases that I presented here, we don't tend to need very many rounds of that, so it's reasonably computationally efficient. And that's why, for example, we were able to see the speed-ups relative to this defoam aeronautics-based optimization procedure using a graph neural network of 10 to 48x is exactly because they're actually surprisingly efficient. So I think that they're pretty compelling from that perspective. Thank you.
Another question in the room?
Great talk. So I have a general question about where the training data come from, because I think you showed a picture of like a video of where you have a bunch of points dropping on a platform and they just kind of scatter. So I imagine that gathering enough data to train the point trajectory model will, at least I believe, will take some effort. So I'm just wondering, do you synthetically generate those data through some of the more analytical simulators, or do you, through some other ways, got those data?
Yeah, it's a great question. So for the GraphNet simulation stuff, it's not actually super data intensive. That's only about 1,000 trajectories of 10 objects being thrown together on a floor. But for the point tracking models that I showed at the beginning of the talk, there's been a lot of work to try to develop better point tracking models, which we were trying to get the autoencoder to work, but we're just taking an off-the-shelf point track producer. But the one that we took is called Boots to Peer by Carl Dorsch and colleagues. And in that model, they actually did use exactly that same data set of objects being thrown onto the ground in order to bootstrap point trajectories. So they used supervised data from that in simulation, and then they bootstrapped it to actually train it on that same YouTube data set at scale. And the details of that are within their paper, but so you don't actually need that much ground truth information to train these point trackers, but that's a sort of existing piece of research that's quite cool. Yeah.
Yeah, thank you very much.
Thank you.
All right, and with that, let's thank our speaker one more time. Thank you, Kelsey.